So welcome to Robotics 2. In today's class, we are going to start a new chapter, chapter 5 on linear design models. And what I will do is towards the end of the class, I will go through the project 3 and discuss the simulation. Over the weekend, I sent you all a Simulink file that contains all the parameters and all the sub functions needed to run a simulation. However, I want to clarify that simulation needs to be modified for the Zagi airplane, and that simulation is a skeleton simulation. You will have to modify and correct it so that you get very good running simulation. And I will talk about it in a later part of today's lesson. But what I want to talk about in today's class is we started with simple equations. Those equations were nonlinear. We added the external forces and moments. And now what we are going to do is we are going to simplify those complicated nonlinear equations so that we can integrate an autopilot loop so that the aircraft can self-control. So next slide. This slide is very important, and I would encourage you to take a snapshot of this slide or save this or refer this, because we will come back to this slide again and again. Believe it or not, this is the equation for the MAV, and these equations we programmed inside the Simulink environment. So what I want you to do is, for a moment, look at these equations very closely. You will see these are 12 first order differential equations. So these are 12 first order differential equations. And we started with all forces is equal to 0, all moments is equal to 0. In the project 3, what we did, we added the forces because of the gravity, aerodynamic forces, and propulsion forces, and we added the moments. And I want you to look at some of these important parameters that are mentioned here. This is the rudder deflection. This is the aileron deflection. This is the elevator deflection. So these are the control surfaces that are controlling the behavior of the aircraft. And you have the external thrust that is provided by the prop and the resulting torque that needs to be compensated so that the aircraft does not self-roll. So once again, I'm going to outline the control surfaces, and these are very important because if you see in the simulation, you can manipulate or change these values of control surfaces gains, and your aircraft will yaw, aircraft will roll, or aircraft would pitch. So essentially, project 3 is simulating these 12 equations with changing delta E, delta A, and delta R, and the thrust. So delta T, which is thrust. Now, before we proceed further, I want to point out these values for aileron deflection, rudder deflection are in radians. So these values are in radians. So make sure that when you turn in your final submission, your aileron deflection, rudder deflection, and elevator deflection are in radians and not in degrees. The sample file that I gave you, I did not make this conversion, but I would expect all of you to integrate this conversion in your file. Otherwise, that simulation will not be correct. The next thing what I want to talk about is you need to choose appropriate VA. Use appropriate VA. And it depends upon where you are flying. So for an example, just to give you an example, you can't have a Toyota Corolla going 0 to 60 in 3 seconds. It's not a Tesla. So similar to that, a simple Zagi frame cannot achieve very, very high air speeds. So what you need to do is you need to pick up the realistic value of VA so that you will have a simulation and of course the animation that makes sense. Otherwise, you are not gonna get a nice simulation that is shown on the website. So these parameters need to be tweaked so that you get a correct working simulation. So once again, project 3 is nothing but programming these equations inside the MATLAB, changing the values of control parameters, and then feeding PN, PEH, UVW, roll, pitch, yaw, etc. to the airframe animation so that the airframe gets animated. However, one thing I would like to tell you, and that is important, is that is about the wind model. So wind models. Now, please understand, depending upon the airframe, you cannot fly an airplane like small MAV at 15,000 feet because that is not the range of that aircraft. You would expect the airframe to fly within 100, 200 feet. So you will have to choose the appropriate values for the wind model, appropriate altitudes for wind model. So choose proper height or altitude. And I would expect that as you refine your simulation, to do some searching, look at some papers and see how this aircraft, Zagi aircraft, is simulated. And I just want to show you very quickly. If you want to look at the references, check this website. On this website, if you go down, there is this Zagi coefficient. I have uploaded the same file in the canvas, and this talks about how the Zagi airframe can be actually simulated. So you are all encouraged to look at this paper to refine your simulation. And if you look at the module, here, the in supplement, you will notice that I have added additional material that can be useful for design and simulation. So I would encourage you to look at these additional resources that will be super helpful as you improve your simulation. So I just want to go back and tell you that don't forget to look at this reference that is given on the UAV uh, website. And this is nothing but this paper. This is the paper. And what I'm going to do is I am going to add this paper, the link of this paper, to the chat window. That may be able to give you some answers to the questions on what coefficients to use, what parameters to choose, and then how do we control yaw from the roll, and so on. So please take a look at this paper and use this information to modify your simulation. So moving on to what we were talking about. In today's lesson, we will be focusing on how do we simplify these equations so that we can implement simple autopilot system. And we are going to start with a linear control, and we will use the techniques that we studied in robotics 1. For example, we will look at the state space formulation. We would look at the transfer function formulation, and we will see how these techniques can potentially be used for solving the problems. Once again, I just want to clarify, there are going to be a lot of equations coming at you in this chapter. All these equations may seem like very complex, but they are not, because what we will do is we'll focus on one equation at a time and part of the equation at a time. At the end of the day, what we want to do is we have these equations of motion that are given here, and somehow we would like to control these equations of motion autonomously. So that is the purpose. So let's start with a very simple approximation for the lift and drag models. So we looked at a nonlinear lift model and we looked at the associated drag model. So we noticed that the lift is linear in certain region, and then what happens is at the stall, at when the angle of attack exceeds certain critical value, the lift drops down. So lift, and this is angle of attack. And you can implement a nonlinear model with blending. So this is the blending factor, and we talked about it. And or what you can do is you can use a very simple linear model. If your angle of attack is not changing much, if your angle of attack is not changing much, then a linear model will be sufficient to give you accurate simulation results. Now, next thing I want to talk about is an important concept which is called as the coordinated turn. And coordinated turn is something called as banking. So you bank, so basically you yaw and roll at same time. And this is a very desired situation. And if you fly by airplanes or if you have traveled by airplanes, you probably have experienced this coordinated turn. Typically, if you land on the Williams airport, which is next to Polytechnic campus, after the mountains to approach the runway, almost all the aircrafts coming from north, they will have to do a coordinated turn so that the aircraft is aligned to the runway longitudinally. So you will notice that aircraft not only turns. So what I want to show you is pure turn is this. Aircraft not only turns, but it also yaws. I mean, it not only yaws, but it also rolls. This is a desired condition which is called as the coordinated turn. The coordinated turn is preferred so that the lateral acceleration on passengers is minimized. It's a very comfortable way of turning the aircraft. And if you look at the big aircrafts, they usually do a coordinated turn. So what happens in coordinated turn? You have a center about which the aircraft needs to rotate. So please notice that aircraft needs to rotate about this. But as the aircraft is rotating, it also banks, it also yaws. So you will see that there is a non-zero uh, roll angle that is along with the yaw. And the way it works is this is something like a centrifugal acceleration. So you will be having the component of force, and this component of force multiplied by the roll angle, component of force, component of lift multiplied by the roll angle gives you the force along the radial direction. So this is the force along radial direction that is compensating the centripetal component of centripetal acceleration. The acceleration multiplied by the mass. So in this particular case, the external reaction force is compensated by the component of the lift force. Now, some of you may just be referring to what is this. So there are two important angles that I want you to notice. One, this angle is called chi, and that angle is called as the coarse angle. We looked at it. And this angle is called gamma, and this is called as the flight path angle. So coarse angle is nothing but if you were to draw uh, the Vg, which is the ground velocity, and then if you look at the angle made by the aircraft, the angle made by the aircraft with respect to the air speed or the forward speed of the aircraft is nothing but the difference. This is the difference between the coarse angle minus yaw. So this angle is coarse angle minus yaw. And you will realize that this difference occurs because of the wind velocity. Since you have a non-zero wind velocity, your ground speed is different than the airspeed. And it will be instructive to just write this equation. So you have the ground velocity is equal to the airspeed plus wind velocity. And I want you to understand that you are going to have a component of the weight along the z-axis, and that needs to be compensated by the component of lift. So component of lift, and I will show you for the reference. This is going to be F lift multiplied by cosine phi. So this equation is important, and with this equation is also important. And these two equations will be used when we simulate or when we simplify the equations. And this condition is called as coordinated turn. And you will notice that for a coordinated turn, the radius of turn is given as this equation. So if you have a coordinated turn, then the radius of turn is given as Vg cosine gamma divided by G tan phi, tan psi cosine of chi minus psi. And this equation will be useful when we try to look at or try to simulate the turning dynamics of a UAV. So please note, just unlike cars, the UAVs don't turn at just like at their current location. So there is a difference between turning of planes and turning of ground vehicles or say cars. So whenever you have a plane or air vehicle turning, there is some role associated with it. But when you are turning car, typically you don't have any role, which means if you try to do a very quick turn, you will notice the car tries to roll, but your car has anti-roll bars or other mechanisms to prevent the vehicle from rolling. So that 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 control scheme or anti-roll bar or torsion bars are not available in the plane. So whenever there is a yawing motion, when the plane is turning, there will be some yaw that you will experience. That's why the coordinated turn is the condition that we look at. Before I begin the next discussion, I just want to make sure that everyone is comfortable with a coordinated turn. So the aircrafts, the planes do not turn in one plane. What it means is aircrafts do not turn like this at its location. When the aircraft turns, the aircraft actually banks a little bit. It yaws. As it yaws, then it rolls and then it turns. When you have a ground vehicle, then you will notice that uh, this roll motion is sort of compensated or not desired, and you have anti-roll bars that would prevent car from turning. That's why when you are driving an SUV, you will see the sticker on the back of the windshield or visor. It says high rollover risk. So be careful while turning, and that is the reason why uh, the aircrafts, when we look at the turning of the aircrafts or yawing of the aircrafts, we look at the coordinated turn. The next part is talking about trim conditions. So trim, this word or this concept is prevalent in the aircraft dynamics. Trim is nothing but equilibrium. Now, the equilibrium for aircrafts is defined slightly differently than the equilibrium we study in statics or dynamics. So typically, when we look at equilibrium, that means all the forces and all moments, whether the aircraft is in static or the object is in static condition or the dynamic condition, are balanced. However, when we are looking at the aircraft, even though not, it is not required for trimming to, to all the state variables to be balanced. In other words, let me explain what it means. So if you have an equation, something like mx double dot plus cx dot plus kx is equal to say f. And what I want to do is I want to find out the equilibrium position. So I want to find out what is the equilibrium position. So the standard technique to find equilibrium position is when the derivatives are zero. So which means kx and x is equal to f by k. This is the equilibrium position. So please note all the velocities and all the acceleration are considered to be zero. But when you look at the trimming, not all the velocities have to be zero. Because if you think about the aircraft that is flying, and if all the velocities of the aircraft is zero, aircraft is no longer an aircraft, it's a rock and it's going to fall down. So for trimming, it's an equilibrium condition, but not all the state derivatives are equated to zero. And this is an important concept. The difference between the equilibrium in statics and dynamics and trimming is if you consider the aircraft to be in static equilibrium, which means all the external velocities and acceleration zero, then there is no forward speed. No forward speed means no lift. No lift means the aircraft is going to fall down. That's why, in general, aircraft in equilibrium is considered to be in trim condition. But trim condition, and this is an important statement, may include the states that are not constant. So in other words, the trim condition is given as some of these states are zero, some of these states are constant, but not all the states are constant. For an example, forward speed cannot be zero. So that's why the trimming is considered when the aircraft is in level flight. So how do we calculate trim? Now, for trimming calculation, few conditions need to be satisfied. First and foremost, for trimming, the aircraft needs to fly at a constant airspeed. So the airspeed is not equal to zero, but airspeed is equal to constant, which means the aircraft does not have longitudinal acceleration. So when you look at airspeed is equal to constant, which means the aircraft does not have longitudinal acceleration. Aircraft has a constant flight path angle. Now, if you look at the definition of flight path angle, and we studied this in last lesson, but I just want to explain it to you what the flight path angle means. You have an aircraft that is pitching, and if you look at the ground path, if you look at the ground velocity Vg, and if you look at the component of the ground speed vector, horizontal component of the ground speed vector, this is the horizontal component of ground speed. This angle is nothing but the flight path angle. So this flight path angle needs to be constant. And the last but not least, if the aircraft is turning, the radius, orbit radius has to be constant. You can't have the orbit radius changing. And what you will do is, when you want to find out the trimming condition for the aircraft, you will substitute these as inputs. So these are the inputs. And in project 4, we are going to study the trimming. So the idea is, if you look at these equations of motion, in these equations of motion, we will substitute those three variables as constant. And once we substitute those three variables as constant and set all the derivatives is equal to zero, we are going to get a coupled nonlinear system of equations. Once again, it's a coupled nonlinear system of equation, and we will try to find out the values of states so that the left hand side is equal to right hand side. And those conditions are called as the trim values. And to be honest with you, finding the trim for a small airframe with lot of approximations is easy, but when you have even a simple airframe like Zagi, find, finding the trim parameters by hand is almost impossible. So what we do is we used a MATLAB function trim to find out the values of trim parameters. So what are the inputs that we are going to supply? If the it's a constant uh, climb orbit, then the velocities, the forward velocities in the body frame are equated to 0. The roll and pitch rates are equated to 0. So what I want you to do is I want you to take a note of this and notice these u dot, v dot, w dot, phi dot, theta dot, p dot, and q dot will be substituted in these equations of motion. So please note, you see on the right hand, on the left hand side, you see these variables. These will be treated as zeros. So once you treat these equation conditions to 0, so think about it, right? We have 12 equations. We have 12 equations. Out of 12 equations, we have seven equations. The left hand side of these 7 equations will be 0. And then if the turn rate is constant, then we will substitute a constant value for this guy. So which is the yaw rate will be substituted as 0. That essentially means the r dot is equal to 0. And then what we do is we solve, and we on top of it we are substituting these values. So that gives us enough number of equations and enough number of constants to solve for the trim equation. So once you try to solve for the trim equation, here is what we are going to do. I want you again to refer to the equations on the first slide. And please note, we are going to substitute u dot is equal to 0, v dot is equal to 0, w dot is equal to 0, phi dot is equal to 0, theta dot is equal to 0. We'll substitute psi dot. Please note, the value for psi dot are known. So these are known values. So we'll substitute this value as constant, this value as 0, this value as 0, this value as 0. And then we will substitute value of h dot, which is the altitude rate, as a constant value. We don't worry about Pn star and Pe star, because please understand these can't be 0. They don't have to be 0. Because if you have your forward velocity and the eastward velocity is 0, then basically you have no motion. So you wouldn't worry about these. What you will do is you will substitute all these in the equations given on the first slide, and then find out the values for the states. And these states essentially are obtained by solving a nonlinear algebraic system of equations. And please note, we don't do this. We use MATLAB to find the solution. And sometimes you may realize that you have to resort to some numerical techniques or special numerical algorithms to find the trim conditions. And sometimes you will also observe that the trim condition cannot be found out for certain combinations of input parameters, because no equilibrium solution exists, or MATLAB cannot find the equilibrium solution within given parameter range. So before I proceed to the next slide, I just want to make sure that everyone understood what do we mean by trim. Uh, so the idea is you have the set of equations derived already. So you already have these set of equations. And trim is a MATLAB command that takes input just like ODE45, which is nothing but the set of equations. And what trim function will do, just like it solves the ordinary differential equation, just how the MATLAB solves ordinary differential equation, it will solve nonlinear algebraic set of nonlinear algebraic equations and give you the values. And I will take an example on how to trim on a simple equation, and then that will give you some help. But if you really want to know how to use the trim command, I would encourage you strongly to look at the appendix, where in appendix there is an example. I will show you. Look at appendix F. There is a Simulink way of solving trim. So appendix F. So it has a Simulink code for solving trim command. It also has the MATLAB code for solving trim command. And that actually is very simple. So with that, we should be able to get the values of trim. Okay, but don't worry, I will take an example in next lesson. Okay, now the next part, I just have to caution you. It may seem complex because there are just equations and equations on slides, but it's not. And I want you to understand the physics behind those equations. All these equations come from these this slide. So all the next equation, the next few slides are going to have lots and lots of equations, but those equations come from these 12 first order equations. So bear with me. Now, here is my objective. I want to ensure that the aircraft is stable in roll. So here is, or somehow I design a controller. So here is the basic objective. Design a controller so that aircraft stabilizes in roll. So this is the basic condition. Here is what I want to do. So the way I'm going to look at it is, first and foremost, and everyone understand, I'm going to start with this equation. And if you look at this equation is nothing but the exact same equation we have over here. So I have this equation, and I'm going to call this equation star. So what I'm going to do is, first I want to stabilize in the lateral direction. That means what I'm going to do is I'm trying to stabilize the aircraft in roll. Now, it may be instructive or it may be intuitive at this time, just to give you the definitions of the stability that we studied in robotics 1. So we talked about something called as the neutral stability. In neutral stability, what you have is the system response does not diverge, does not converge, it remains as is. This is called as the neutral stability. And for neutral stability, the eigenvalues are purely imaginary. Then we talked about asymptotic stability, which means this is like a ball in a cup, wherein what happens is, over a period of time, the response dampens out. And we notice that here the eigenvalues have negative real part. And then it can have plus minus imaginary. We also talked about unstable system, wherein the system response actually grows and the eigenvalues are positive real parts. Now, this is what we studied in robotics 1. Now, let's try to extend those concepts to the roll stability. What it means is I want to think about a hypothetical situation. And I want you to think about that I have an aircraft that is flying in a level flight. So this is an aircraft. This is a tail, nose. Now what I want to do is, if for some reason this aircraft is disturbed from its equilibrium position or if from its trim position, what I want to happen is I want this aircraft to come back to its original position. So this aircraft needs to come back to its original position. So the aircraft, if you think about it, the aircraft got disturbed, but then still I want it again to come back to its equilibrium position. So I want asymptotic stability in the rule. So the idea is the differential equation that we are looking at, I need to make sure, and this is an important statement. So the differential equation that we are looking at is a differential equation, something like phi dot is equal to P plus Q sine phi tan theta and r cos phi tan theta plus r cos phi tan theta. At the end of the day, I want this differential equation to be asymptotically stable. And depending upon what are the values of P, Q, phi, theta, phi, tan theta, this equation may or may not be asymptotically stable, which means the eigenvalues of this differential equation may or may not have negative real parts. So my objective, whether I function or state space, and I want to make sure that the eigenvalues of this differential equation have negative real part. So that is what I would like to ensure from my controller. Now, one thing I want to talk about here is what controller do I have available for controlling roll motion. So clearly, let's talk about the control surfaces here for a minute. So if you have an aircraft, the roll is typically controlled by the ailerons. So ailerons are the flaps on the wings. So once again, this is the aircraft, and ailerons are the flaps on the wings. And these wing flaps, what they do is they change the differential lift, and the differential lift causes the aircraft to roll back. So the control surface that I'm going to use, so control surface, primary control surface I'm going to use is aileron. And how is this control surface aileron is defined? Control surface in aileron is defined by means of delta A. So now what I want to do is I want to change this equation or append this equation with a control surface so that the eigenvalues of this equation, they will have negative real part. That is what we are going to do in control. And please note, transfer function technique is only applicable for linear systems. So when you are trying to control a system in using transfer function, and I need to discuss this once again, transfer function, we studied this, is the Laplace transform of output divided by the Laplace transform of input. So what we do is, if you have a differential equation x dot, when we take the Laplace transform, it becomes Sx. If you have a differential equation which is x double dot, when you take the Laplace transform, it becomes S square x. So the idea is, I'm going to take this differential equation, I'm going to take a Laplace transform, and then I'm going to add a control surface as an input so that this roll motion of the aircraft can be controlled. However, you will notice, and we will talk about a little bit later, that because of the complicated dynamics of the aircraft, the pure control may not be achieved because it's actually coupled with pitch as well. So let's go back, and then I will go through this very slowly, the control algorithms. But I want you to understand these from the physics point of view, not from the mathematics point of view, because I completely understand these equations may seem daunting. All right, all said and done. What I'm going to do is, I'm going to take this equation star, and I'm going to differentiate the left-hand side and the right-hand side. But before I differentiate this, what I'm going to do is, I'm going to do a trick that is commonly used in control design, is treating a complicated part of the equation as a disturbance. Now, please understand, this is a trick. Again, this is a trick that is used when we design the control. And if you have not seen this before, this may seem like a voodoo, but don't worry, this is a commonly used technique in control. So let me explain what it means. I want you to focus on this second term. This second term shows me the coupling between the pitch and the roll. So as you note, this is the pitch angle and this is the roll angle. So what this shows me, it shows me the coupling between the pitch and the roll. Same thing happens over here. The second term also has a pitch and roll coupling. Now what I'm going to do is, this term, it's clearly nonlinear because it is the product of cosine and tan. It's a product of sine and tan. So these two guys are nonlinear. So for control design, I'm going to treat this nonlinear term as a disturbance. So for control design, this nonlinear term is treated as disturbance. So this is important. Nonlinear term is treated as disturbance. Now what it means is, this equation gets simplified, and I want you to follow this very carefully. This equation gets simplified into this, wherein you have a phi dot is equal to P plus this disturbance. And this disturbance is this big nonlinear equation. Now what I'm going to do is, I'm going to take this equation and I'm going to call this equation 2, and I'm going to differentiate this equation, the left hand side as well as right hand side. So as soon as I differentiate this equation, please note, I get phi double dot, I get P dot, plus I get D phi 1 dot. Some of you may ask me, why is this differentiation required? And please pay attention, because we have an explicit equation for P dot. So please notice that if I go back all the way to my equations, I have a nice equation for P dot. This equation is for P dot. That means when I differentiate, I'm able to substitute the equation for P dot in this equation. So when I substitute, I'm able to substitute the equation for P dot in this equation. And that's exactly what happened here. So you will notice this guy from all the way from here to here is nothing but P dot. And then as soon as you add P dot to it, what happened? Notice the control surfaces came into picture. So as soon as I added P dot, then please note here, all these are constant. So I'm going to show constant with, so this is constant, this is constant, this is constant, then this is constant, 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 this is constant. So all of a sudden, the control variables came into the picture. Now what it means is this allows me to tune the eigenvalues of the differential equation. So it allows me to tune the eigenvalues of this differential equation the way I want using the control input. What it means is when I carry out this simplification, I want you to notice this entire equation is now expressed in terms of aileron control surface, rudder control surface, and I have these small terms that comprise of the derivatives of the nonlinearity, which means I have a very simple, super simple differential equation. I have a very super simple differential equation, which is phi double dot is equal to a constant multiplied by phi dot, another constant multiplied by the aileron deflection, and then this is the nonlinear disturbance. So this is the disturbance. So what it means is by taking the derivative, it allowed me to use another equation to substitute in the differential equation of motion and simplify the differential equation so that now the control input, which is the deflection of aileron, appears in the differential equation. And what I want you to do is, I want you, for a moment, let me give you sort of an intuitive feel for what this equation is. And I want you to notice how this equation looks. So intuitively, you have phi double dot plus a constant phi dot is equal to a, a constant a phi 2, which actually depends upon phi and delta a. Let's assume the disturbance for the time being is 0. So what it means, I could change the eigenvalues of this differential equation by changing the value of delta A. And that is all there to it when we talk about the lateral transfer function control. In other words, this allows me to relate the aileron deflections. It allows me to relate aileron deflections, delta A, so that I can control the aircraft in a fashion I want. So how is it implemented? Let's talk about a very simple transfer function implementation. So what I'm going to do is I'm going to have my input. I'm going to have my input as aileron deflection, and my output is nothing but the roll angle. My input is aileron deflection and my output is nothing but the roll angle. So what it means is this equation. Now I'm going to take the Laplace transform. This is going to become S capital Phi of S is equal to minus A phi S capital phi of S plus, then I'm gonna have these a theta, a phi 2 and d phi 2, all these terms. So what it means is I want you to look at final equation is output. This is my output and my input is this. And please note, since I have this disturbance floating around, my input is gonna get disturbed by this disturbance. So this is disturbance. And somehow I need to make sure that this transfer function is designed in such a way that my capital phi of S behaves in a controlled fashion. So that is how the roll dynamics will be controlled. Now, this may be a little bit of too much if you have not seen this material before, but here is what I want you to understand. Physically, from physics point of view, this is your controller input. This is your control. But unfortunately, the control is not pure. You are going to have some nonlinear disturbances that is going to change the actual value of control. And this control, along with this nonlinear disturbance, will act on this transfer function. The control, along with this disturbance, will act on this transfer function to give you variation in the roll. So this is the roll angle. And however, what you need to do as control designer, you have to select or you have to choose the values of a phi 1 and a phi 2. You have to choose the values of a phi 1. Please note, a phi 1 appears here and a phi 2 appears here. You have to choose the values of a phi 1 and a phi 2 so that the system is asymptotically stable. And that is all this control in the role is. Okay, now what I'm gonna do is I'm gonna stop here and I will continue this discussion again in next class. And I'm gonna discuss the project. But before I do that, are there any questions? Any questions? Okay. Now what I'm gonna do is I'm gonna go back to the MATLAB script that I shared, and I will discuss how that script works line by line. So all of you, so before I proceed, I just want to make sure, were you able to get this system simulation working? I shared the code. I emailed the code and I uploaded the code on the canvas. Okay, so I see here. Oh, by the way, I just want to tell you that everyone sees the private message. So please don't send any private message. So, okay, I just want to show you how this code is implemented. And please note, this code is not complete. Once again, the code is not complete. You will have to modify the code so that it runs properly for your airframe. First and foremost, I'm going to start with derivs 1. This is the same function that we have been playing with. So if you look at this function, this is exactly the same function, but here is the difference. There is no external force. We are supplying the external forces that are calculated in runtime. Other than that, this is the exact same code. This derivatives 1 is the same code that we used. Next thing I want to show you, this integrated MATLAB function is the same draw aircraft function that we used. There is this external clock. Now here is the difference. So what I'm doing is, when we are integrating this, these external states are fed from here all the way to the states. But please note, these F states that we supplied as 0, now these F states will be fed from the output of forces and moments. So let's take a look at quickly what forces and moments function is doing. This is the exact same function we dissected in last class. This function has an input x, it has the control variable input and wind speed. Please note, this delta has to be in radians. So you will have to add suitable gain so that this delta is converted. This delta is converted into the radians. So you can either add a gain term over here, which is pi by 180, or you can add a gain term in your Simulink block. But elevator, aileron, and rudder, these need to be converted to radians because that is how the implication is. Ghazi, I emailed everyone the working simulation. So now there is this wind speed. There is no other change in the code except I want you to notice that UAV parameters.mav underscore b underscore c, those now should be corresponding to Zagi. So you will have to change these corresponding to Zagi. And this rho is the density of the air. So this rho will be something 1.2 or 1.3. So please make this change. For kicks, if you try rho is equal to 1000, you will notice that your simulation will be unstable because that is not the correct density. So the forces that you'll apply will be enormous. Now here you have force underscore 1, force underscore 2, force underscore 3. All this code is exactly the same. No changes in this code at all, except for the fact that you will have to make these angles in radians. No change in throttle. Throttle limit is from 0 to 1. Now let's look at the next part. I want you to understand there is a lot stuff here. I added some additional information so that you can send data from the command window. You can send data from another Simulink file, or you can actually run a MATLAB file that can run the simulation. So what I want you to note is input to the force moment function is the state x. So this x is tapped from here. So can you see these states? They go here, and then I'm tapping these states and feeding it to force moment block. It also needs the rudder, aileron, and throttle information. So that is coming from here. Please note, this gain is incorrect. This is shown in degrees. This needs to be converted to radians. Then you have this wind value. This wind value, there are two parameters to this wind value. One is the value of wind that is steady state. So the steady state wind value comes from here. Also, please note, this is incorrect wind value because this wind value, the steady state wind value, is very small. So you will have to substitute the appropriate wind value to come up with a realistic simulation. This indicates that the wind velocity is very, very small. That may not be the case. Now, this is the constant part of the wind, and you have the gust part of the wind. That comes from this Dryden model. This Dryden model has an input. You have certain value of h. Please note, this value of h is incorrect this value of h is 50 meters. You will have to substitute the appropriate value of h to get the good estimates on the gust. Now, then you will have to substitute airspeed, which is VA. Please note, Zagi will never reach 1000 meters per second. Zagi will never go to the airspeed of 1 kilometer per second. So you will have to change this value of airspeed appropriately so that you get good wind parameters. This direction cosine matrix will be identity because we are taking care of direction cosine matrix in this model. Now, what you have is you have the wind gust and you have the angular velocity of the wind. These velocities can be observed on this scope. So you will have 6 parameters, the linear velocity and the angular velocity on the scope. This information is fed over here. The output of this force movement block can be seen either on the command prompt. Wind velocity. So you have to be consistent. The wind velocity should be in the same consistent unit as P. Yeah, to find the realistic values, look at the paper that I referred. So look at this paper, and that will give you some realistic values for the Zagi, that airframe that was flown. Okay. Now, if you look at, yeah, I will answer this question in a minute, Zagi. Ghazi. Sorry. So your airplane is Zagi. So what you need to do is you need to grab the output of this force moment. The output of force moment is actually 12 parameters. So look at the output of force moment. After those first 6 parameters are nothing but the forces and the moments, and you have to be super duper careful. So you should have force 1, force 2, force 3, Fx, Fy, Fz, and then you will have L, M, and N. Don't change this order for multiplexer. Your results are going to be wrong. And all this information is fed back to F state. And then here, all these values are also shown. When you run the simulation, if you run the scope block, you will notice it shows all the information. And all my states are plotted, so it seems like a cluttered plot, but I would strongly recommend you to separate out the positions, velocities, and orientation. So you will know how far the aircraft is flying, what are the values for the aircraft. You may not be seeing a good animation because the aircraft does not have significant travel in X, Y, and Z direction. If your simulation is causing your MATLAB to crash, you will have to change the simulation parameters by going over here, modeling, model settings, and you will have to tune the simulation parameters here. And I don't know what is your configuration, but I promise you that there were 2 students who had their simulation crashing, but then they freed the RAM and then they change certain parameters. They change the solver, the step size, and then the simulation stopped crashing. Your simulation should not crash if you are using MATLAB 2020. Now what I'm going to do is I'm going to run the simulation. So click on the run, and so you can see this airplane. As you change the aileron gain, so let me show you both. As you change the aileron gain, you will see that aircraft is going to rotate, and it's rotated along aileron. But please note, there is a rudder gain too. So if you change the rudder gain, you will see that the aileron and rudder together, it actually creates a coordinated turn. If you want to change the elevator gain, you would change the elevator gain. And now you can see clearly the aircraft has become unstable. So what you can do to start, you make it 0. Please note, this simulation is incorrect because these values are in degrees, but your values need to be in radians. And this simulation is shown if you change your throttle gain to 0.1, which means you will notice gradually the plane sort of becomes stable. One thing that you may ask, why isn't this aircraft going up or down? And the reason for that is, look at this scope block. You will notice the altitude that is gained by the aircraft is hardly 20-25 meters. So it's hardly 60 meters. And if you look at the scale that we have is all the way from 2000 to minus 2000. So you are not going to see an appreciable change with respect to the input. I would strongly recommend that you play with the parameters, play with the gains. For an example, this VA, airspeed is not right. Zagi will never go to 1000 meters per second. So you change this airspeed, and what would help you is the reference that I gave you here. So this reference will tell you what are the typical parameters that you can expect on the Zagi frame. And then you will you should be able to see and upload a very clean, nice working simulation. Please note, this is just the beginning. If you really want to create your own game, what you can do is you can map this elevator gain to keyboard input like left arrow and right arrow. You can, or A and S, or E and X, or R and F. You can actually map this input to your keyboard, and this will be like a flight simulator. And that you can actually fly your own plane in the MATLAB environment. Once again, the values that this airframe is using is for Aerosonde. That is not right. So to make your simulation run properly, you will have to use the airframe values for Zagi. Now you see I changed the elevator gain and the aircraft is back into the level flight. Okay, I'm gonna stop here, but I'm gonna ask if there are any questions. Now aircraft is climbing, I want stop. If I want aircraft to stop climbing, I would change the values of the elevator gain, and you will notice, oh, this is too less, and the aircraft will actually go back to its own. So now aircraft is doing a flip. All right. So with this, I want to ask if there are any questions. Yes, Bao, what is your question? You want me to unmute you, or do you want to type your question? So if you want me to unmute you, yeah, let me see. You can raise your hand. Bao, yeah, I saw Bao. Here, Bao, you are unmuted.
Can you hear me?
Yes, I can hear you.
So I want to ask that on the project, question number 3, to verify your simulation by setting the control surface deflection to different values. So how do we prove or show that in the project
Okay,
when we submit it?
good question. And that is shown over here. Can you see my screen?
Yes.
So look at chapter 4 sample simulation. Please note that they implemented the simulation completely differently. So their code is written in S function, but it's implementing the exact same thing what we have. And now observe, you will notice that the author changes the aileron rudder gains, and you will see that the control surfaces, can you see? The aircraft is pitching down. And you see all the values of the climb and the roll rate, pitch rate is seen over here. Does it
So,
answer your question?
do we need to record a video that we're changing the number?
So here is a, if you can record a video and upload it for Mannath's reference, that would be really good, because that way he can verify. So what Mannath is going to do, and I think Mannath is online, he is going to run your simulation to make sure that it shows what is shown over here. But I would strongly recommend that if you record it, upload the recorded videos along with your solution. That way Mannath knows that, hey, your simulation is working and there won't be any question. Everyone
Okay.
understood this?
Yes.
Okay. Now let me answer John's question. John, I think I answered this question in last class, but I will answer this question again. If you change these initial conditions, say for an example, if you change this initial condition to 100 or say 1000, your aircraft will start at a different location. And to answer Michael's question, Michael, you'll have to go to model settings and then change these settings here, double click, and then make sure that your system is able to run. So, okay, Anson has a question. Okay, Anson, do you want to share the screen in front of everyone, or you want to show it to me later in a uh, separately? If you want to show your screen, I will be happy to make you, let me make you Anson. Anson, now you are a co-host.
Right. Yeah, I can share it in front of everyone. It doesn't matter.
Okay.
So when I run it, my aircraft is unstable.
Correct.
And I just wanted to verify. The parameters that I've pulled were from Appendix E.
Yeah.
And I've been playing around with it, but it's continued to be unstable. And the main thing I've noticed is that my angle of attack shoots up from like -100. And my forces and moments, as well as my derivatives files, are pretty much the same as yours. I just wanted to verify that this issue is specifically due to not me needing to tweak my parameters and not like a calculational error.
So actually, I would refer you to this PDF file and read through this. Let me tell you, the aircraft that we are using, okay, is inherently stable. If you look, so what might have happened is either plus or minus sign in coefficients. And the second thing that I want to talk about, and this is important, and actually I don't want to give out the answer because this is something that you guys have to study. Control of Zagi is slightly different than the control of Erosonde. So if you think about the Zagi does not have a rudder per se, but the ailerons, when they act together, it acts like an elevator. When the aileron, they act in the opposite direction, it acts like an aileron. So basically what they have is nothing called as ailerons. So what is missing in your simulation and is the mapping here. And if you ask me what type of mapping it would be, I'm going to refer you to the textbook on the control surfaces of the Zagi airplane. But let me tell you, you are on the right track. And if you implement that mapping correctly, then you will see a very nice, stable Zagi plane, as
Okay.
discussed the text, as discussed in the PDF file. So my suggestion to you is read through the textbook chapter, watch the material where we discuss the control surfaces for Zagi, and read through this paper, and you will be able to tweak your simulation so that it will look very nice.
All right, great. Thank you.
All right. Any other questions?